So we are from BSIT 3B BPO. So in this video, this is about Diffie-Hellman key exchange algorithm. So what is about in this algorithm? So Diffie-Hellman key exchange algorithms were created by Whitefield Diffie and Martin Hellman in 1976 to solve a problem of key agreement and exchange. It's allowed two parties that want to communicate to agree on a symmetric key, which may be used for both encryption and decryption. Note that the Diffie-Hellman key exchange technique can only be used for key exchange, not encryption or decryption. Mathematical idea behind the algorithm. Let's move to Diffie-Hellman key exchange algorithm for key generation. So the algorithm is based on elliptic curve cryptography, a method of doing public key cryptography based on algebra structure of elliptic curve over finite fields. The DH also uses the trapdoor function, just like many other ways to do public key cryptography. So this is the example of this algorithm. So as you can see in the top, that is called the third party. The third party also listened to their conversation, so he got the key from Sam that will deliver to Tom, and that is pointless to do. So in this next picture, as you can see, the third party got already the colored key from Tom and Sam. So Tom and Sam select their own colored key and they keep them to themselves, and they mix it together to form this color orange tan and light blue, and they share each other their mixed color key, and they put back their first choice colored key and they mix it together again, and it will be a yellow brown key that the third party will be difficult to get the secret color from Tom and Sam.
So now I will tell you an easy way to understand how Diffie-Hellman key exchange algorithm works. Now let me actually tell you guys what exactly is Diffie-Hellman. So Diffie-Hellman key exchange is also called exponential key exchange and is a method of digital encryption that uses numbers to raise to specific powers to produce the decryption keys on the basis of components that have never directly transmitted, making the task of a would-be code breaker mathematically overwhelming. So basically, the Diffie-Hellman key exchange method allows parties that have no prior knowledge of each other to jointly establish a shared secret key over an encrypt subsequent. Communication using a symmetric key cipher, it is one of the most important key exchange algorithm, which is widely used to secure a variety of internet services. Although Diffie-Hellman key agreement itself is a non-authenticated key agreement protocol, it provides the basis of a variety of authenticated protocols and is used to provide forward secrecy in transport layer security (FML) modes, referred to as EDH or DHE, depending on the cipher suit. The method was followed shortly afterwards by RSA, an implementation of public key cryptography using asymmetric algorithms. Alright, that was a brief about the Diffie-Hellman, and I hope you guys have followed so far because I think it's been an easy ride and I've tried to keep it simple as possible, but you must be knowing that cryptography needs number. So our next segment is all about cryptography and numbers, and assuming that you are comfortable with modular arithmetic.
So let's get started. So the simplest and the original implementation of the protocol uses multiplicative groups of integers called modulo. Now, the foremost step is to assume a prime number. So let's call it Q. Now, After assuming a prime number, we have to select alpha such that alpha must be the primitive root of the chosen prime number, and alpha should always be less than q. So two condition has to be satisfied. So now, what exactly does it mean to be primitive root, and how do we exactly find this? So alpha is considered to be a primitive root of q if the following series is actually followed. So as you guys can see on the series is that alpha mode q, following which is alpha square mode q, following which is alpha cube mode cube, until alpha raised to q minus 1 moded by q. So all this should actually give you a result of 1, 2, 3 till q minus 1. So if this condition satisfy, we call this alpha a primitive root of q. Now, after selecting alpha, the next step is to find the private and public keys of the sender and receiver. So the first step is to actually assume private key of user A now. While assuming the private key, we have to make sure that it is less than q. And then we go on ahead to calculate the public key of user A, which is denoted by y, A out here, and is given by this formula. So to calculate the public key, we use the formula which is alpha r raised to the private key of the user moded by q. Similarly, we also do this following step for user B. So for use of B, we again have to assume the private key, and the private key also out here has to be less than q. Now, we go ahead and calculate the public key of user B, which is given by pi b, which is equals to alpha raised to the private key of the user B modeled by q. So after the following these steps, what user A has is his public and private key, and what user B has is his public and private key. So after this, the only step that remains is key generation.
Now let's generate the keys. The keys are generated at both sides, meaning both the sender and the receiver side. But first, let's observe the information that the sender has. The sender has one private key and sends a bean publicly, which is available on the network, and lastly, the prime number q that we have selected. The sender key is formulated by this formula, which is k, that is the key, which is YB representing the public key of sender B raised to the private key of sender A modded by Q. On B side, we have X is private key, Y is public key, and the prime number Q. So for this, the key is generated by YA, which is the public key, raised to the private key of B and modded by Q. After the calculation of both sides, we have to make sure that the keys are the same. And that is pretty much the theoretical and formula aspect of it. Now we are going to implement it. In symmetric key encryption, whatever the key we are using at the encryption side, we also have to use the same key on the decryption side. Essentially, we are not exchanging the keys, we're just generating keys at both sides, which is the sender and receiver side. Let's get started by considering a prime number, and in this case 11, so q is equal to 11. Now to find the primitive root, and to do so we are going to use a table. Here we have the rows, which are the numbers to be raised, and the columns are the indices. And we are going to use this formula, a raised to x mod q. So a resembles the column that has 1 to 7, and x resembles the row that has 1 to 10. And we have to keep in mind that x can only be q minus 1, so we'll only go up to 10. The first formula will look like this: 1 raised to 1 mod 11. So 1 raised to 1 is the first bracket, and then this whole thing is modded with 11. And then this part will change to 2, then 3, then 4, until 10. When you raise 1 with 1, all of this is going to be 1. Next is 2 raised to 2 mod 11 is 2. Now 2 raised to 2 mod 11 is 4. Mod 3 is 8, and 2 raised to 4 mod 11 is then 5. Then 2 raised to 5 mod 11 is 10. Then 2 raised to 6 is 9. And this is 7, this is 3, and this is 6, then 1. The table shows that our condition is being fulfilled by 2. And the condition was that the result of the formula would be lesser than q, and everything in the table is indeed lesser than 11. The conclusion from this is that a can be 2, that is, 2 is a primitive root of 11.
Okay, so now that we have the prime number and its primitive root, it's time to calculate the public key and the private key for A and B. So here is the A. So let's assume that the private key is for A is equal to 8, and here the public key is equal to 2 raised to 8 modulo 11 is equal to 3. Here we have the, so now we have the private key for 8 and 3 for public key. And now let's begin with the B. So let's assume that the private key of for B is equal to 4, and public key is equal to 2 raised to 4 modulo 11 is equal to 5. So now we have the private key is 4 and the public key is 5. Now let's begin with the calculating of for the key. So here K is equal to, which is the 5, which is 5 is for public key for B, and raised to private key for A is 8 modulo 11 is equal to blank 5 raised to 8 is 390,000 modulo 11 is equal to 4, and for the next key is equal to, which will be the public key of A, which is 3 raised to the private key of B, which will be the 4 modulo 11 is equal to, here 3 raised to 4 is 81 modulo 11 is equal to 4. So as we just proved that the K is equal to K, the 4 is equal to 4. So we have successfully generated the Diffie-Hellman key for these two users. So that's Diffie-Hellman algorithm works. Thank you.